In Earth's ancient seas, giants weren't rare. They were the rule. Fish longer than school buses, armored predators with jaws that could crush steel, and shelled creatures the size of cars prowled waters far richer than anything alive today. These immense forms weren't freak accidents. They were the result of oxygen-rich atmospheres, greenhouse-warmed oceans, and vast, shallow habitats that made supersized life not just possible, but inevitable. To understand why nothing alive now comes close, we need to see how lost environmental forces created a world where being massive was simply the best survival strategy. Atmospheric oxygen did not always hover at today's familiar 21%. In some prehistoric intervals, atmospheric oxygen rose to 30 or even 35%, according to Robert Berner's geocarbsulf model. These spikes transformed the chemistry of the seas. Higher oxygen in the air meant more dissolved oxygen in surface waters, especially across the vast, shallow seas that blanketed ancient continents. For marine life, this difference was more than a number. It was a physiological game changer. As animals grow larger, their bodies demand more oxygen, but the surface area available for gas exchange does not keep up. This is the diffusion bottleneck, a point where oxygen simply cannot reach deep tissues fast enough to support a giant body. When the partial pressure gradient between water and blood steepens, thanks to higher dissolved oxygen, more oxygen can diffuse across gills or skin, and circulatory systems can deliver it deeper and faster. In these high oxygen ages, the ceiling on viable body size lifted. Suddenly, the metabolic math worked for giants, allowing creatures to grow to sizes that would suffocate under today's conditions. Ancient oceans were not just richer in oxygen, they were often warmer too. Surface waters in the Devonian, late Permian, and early Jurassic frequently ran several degrees hotter than today's tropics, sometimes reaching the low 30s degrees Celsius. For cold-blooded marine animals, this warmth was not just comfortable, it was a metabolic accelerator. Biologists describe this with the Q10 rule. For many ectotherms, a 10 degrees Celsius increase in temperature can double the rate of chemical reactions in the body. A 3 to 5 degree increase could speed up metabolism by 30 to 60%. That meant faster growth, higher activity, and a greater ability to recover from injury or predation. Warm, shallow seas covering ancient continental shelves acted like vast incubators, fueling rapid life cycles and supporting dense populations. In these conditions, energy moved quickly through food webs, and creatures could reach sizes and growth rates rarely seen in today's cooler, deeper oceans. The combination of heat and productivity gave prehistoric giants a powerful edge. Ancient continents were often submerged beneath shallow seas that stretched for thousands of kilometers. These eperic or epicontinental seas transformed the planet's geography, creating superhabitats, unlike anything in today's world. The Cretaceous Western Interior Seaway, for example, split North America from the Arctic to the Gulf of Mexico, spanning nearly 1,000 kilometers across at its widest. Sunlight penetrated every corner of these shallow waters, fueling dense blooms of phytoplankton and supporting layers of life from the seafloor to the surface. Unlike the deep, cold basins that dominate modern oceans, these broad sunlit shelves recycled nutrients rapidly and kept the food web tightly packed. With millions of square kilometers of productive habitat, the carrying capacity for life soared. Populations of filter feeders, grazers, and predators could grow far larger, both in number and in size, than in today's fragmented coastal zones. The sheer scale of these ancient seas set the stage for an explosion of marine biomass, laying a foundation for the rise of giants. Energy in the ancient ocean moved through an intricate web of life, with each link in the food chain supporting the next. At the foundation, dense blooms of phytoplankton and algae captured sunlight and nutrients, producing a surplus of organic matter. This abundance didn't just feed small grazers, it set the baseline for everything above, from filter feeders to apex predators. In these productive seas, energy transfer between trophic levels was remarkably efficient. Each step up the food chain, herbivore to small predator to giant hunter, retained enough energy to support bodies far larger than what is possible in most modern ecosystems. Lead Sichthys problematicus, a Jurassic giant, exemplifies this trophic funnel. Stretching 16 to 22 meters, this fish filtered plankton from the water, bypassing much of the energy loss typical in longer food chains. Instead of relying on a cascade of predation, Leadsichthys tapped directly into the ocean's primary productivity, converting vast amounts of microscopic life into massive biomass. The sheer scale of these ancient filter feeders shows how a rich, layered food web, powered by high baseline productivity, could sustain giants not just at the top, but throughout the marine ecosystem. Predator and prey did not just get bigger by chance. In prehistoric oceans, size was a moving target, pushed upward by a relentless evolutionary contest. This is the arms race that Michael Benton describes. As prey species developed thicker armor or became faster swimmers, predators that grew larger gained a clear advantage, with more powerful jaws, greater reach, and the stamina to chase down hardier meals. Over millions of years, this feedback loop created a world where being bigger was not just an option, it was a survival strategy. Cope's rule captures this trend. Across many marine lineages, average body size crept upward through evolutionary time, not in a straight line, but in bursts whenever the environment allowed. The fossil record from the Devonian shows the rise of Dunkleosteus, a placoderm fish measuring 6 to 8 meters long with jawbones that could shear through bone and shell. These giants did not appear in isolation. Each leap in prey size or defense triggered a countermove in predators, ratcheting up the upper limits of what was possible. The result was a marine ecosystem where escalation became the rule, and giants like Dunkleosteus were the outcome of countless rounds of evolutionary one-upmanship. Gigantism in prehistoric seas wasn't limited to backboned predators or filter-feeding fish. Even animals with completely different body plans, shell-bearing cephalopods and armored arthropods, scaled up to daunting proportions. Orthocone nautiloids, studied by Stefan Kroger, stretched their straight shells to lengths of 8 or even 10 meters. These ancient cephalopods engineered buoyancy with internal chambers and a siphuncle, letting them float and maneuver despite their size. Water supported the weight, and high oxygen levels helped their soft tissues keep pace with the demands of a giant shell. Meanwhile, the largest arthropods ever discovered, eurypterids known as sea scorpions, prowled the warm, oxygen-rich shallows. Paul Selden's analysis of Jacalopterus rhenanii, reconstructed from a 46-centimeter fossil claw found in Germany, points to a creature more than 2 meters long. In water, the exoskeleton's weight was manageable, and abundant oxygen allowed their gills to deliver enough fuel for active hunting. These giants show that when environmental filters were removed, evolution found multiple mechanical solutions to the challenge of growing large, proving that the drive to gigantism spanned far beyond the vertebrates. For most of Earth's history, the ocean was a world without human interference. No nets swept the seas, no engines chased the largest swimmers, and no chemicals drifted through the food chain. In this ancient arena, the only limits on size came from physics, physiology, and the environment itself. Giants could thrive for millions of years, growing as large as the ecosystem allowed. This stands in stark contrast to today's oceans, where the impact of human activity is obvious in the shrinking bodies of once abundant species. Atlantic cod, for example, were once legendary for their size, some over 1 meter long and weighing more than 40 kilograms. But decades of intense fishing have driven a rapid shift. Modern cod now mature much smaller and at younger ages, a textbook case of fisheries-induced evolution. The largest individuals are removed before they can reproduce, and the genetic legacy of giants fades within a few generations. In the prehistoric sea, such artificial filters never existed. Evolutionary experiments in size could play out for eons, unchecked by human hands. At the close of the Permian, the ocean's chemistry turned hostile with alarming speed. Widespread anoxia swept across the seas, stripping oxygen from waters that once supported giants. Sediment cores from Meishan and Graphite Peak record this catastrophe in layers of black shale, evidence of lifeless, oxygen-starved depths. Within a geological instant, between 81 and 96% of marine species vanished. The largest animals, with their high oxygen demands and slow reproduction, were hit first and hardest. Our Joey Twitchett's analysis shows that as oxygen levels crashed and food webs unraveled, giants starved or suffocated before smaller, adaptable forms. In the aftermath, only modest survivors remained. The ceiling on body size, once lifted by abundance, slammed shut almost overnight. Today, the largest marine giants exist on a far smaller scale, their ancient conditions erased by extinction and human impact. Our oceans are quieter, but also more fragile, reminders that the balance sustaining life's extremes is never guaranteed. What vanished once can vanish again unless we understand what's at stake.